Okay. Thank you. Well, it's a pleasure to, okay? It's a pleasure to be here in Moscow. In fact, this was my dream to come to Moscow for 40 years. I went to Budapest in 1976, and then I went to Eastern Europe many times, and I always wanted to come to Moscow. And thank you, Andre. Here I am. It's very good. So I will give 4 lectures. This one will be a more general lecture with mathematics in it, but also I want to talk about a very special person, about Paul Erdős. Paul Erdős was a giant of 20th century mathematics. He worked in many areas of mathematics, but today I want to talk about a single area that he worked in. It's called the probabilistic method, but more and more I like to call it Erdős magic, and we will see the reason why. But also, Paul Erdős was a very powerful mathematician, but also he had a very special spirit to him. He had a soul that was almost Russian, we can say. That he had a special spirit, and maybe I can tell some stories about him. I think that this quotation from Fan Chung, one of his leading female collaborators, she is a professor at University of California at San Diego, and I think this gives some of the spirit that we all felt when we worked with Erdős. So, what do I do? Go here. What? Mm-hmm. Good. Okay. Erdős had a unique lifestyle. There are many famous quotations from him, but this one I think is my favorite. I have no home, the world is my home. That is how he lived. Beginning in perhaps 1947 until his death in 1996, he just traveled from place to place. He would come to my house, and he would stay for 3 days, and then he would get on an airplane and he would fly to Melbourne or Bonn or anywhere, and he just kept doing this for 50 years. It was really an amazing lifestyle. Of course, every place he came, we were so excited. So for 3 days, we worked on mathematics, and then he would go somewhere else, and then the next 6 months, we would try to really understand it and to write down the results. In 1947, Erdős wrote a 3-page paper in the Bulletin of the American Mathematical Society that opened up this new area, this new method called the probabilistic method, or what I like to call Erdős magic, with the following theorem. Some of you will recognize that this is from Ramsey Theory, but you don't have to know Ramsey Theory to understand that if n choose k2 to the 1 minus k choose 2 is less than 1, then by k sub n, k is for complete. It means n vertices and all n choose 2 edges. So you have the complete graph on n vertices. You color the edges, not the vertices. You color the edges red and blue in such a way that there are no k points where all the k choose 2 edges are the same color. So if you are familiar with Ramsey theory, that says that the Ramsey function of kk is greater than n. But it stands by itself. And today we give the proof in 2 words, just color randomly. So the idea is we consider a randomized coloring. There's each color, you just probability 1/2 it's red and 1/2 it's blue. Now for any k points, the probability of failure so here you have n points, and for any k points, they might all be the same color, but the probability that they are monochromatic, so the algorithm is color randomly. That's the whole algorithm, randomized algorithm. But it might fail. The probability of failure is 2 to the 1 minus k choose 2. It's k choose 2 coin flips. They're all the same. And so the probability that the algorithm fails, for the algorithm to fail, it's the disjunction of these events. Now, actually, the probability of a disjunction is very difficult, but we only say the probability of a disjunction is less than or equal to the sum of the probabilities. Seems weak, but we get surprisingly strong results. So this is less than or equal n choose k. Oh, I think, how do you write n choose k? C.
Below and k is.
Okay, sorry. This is. These are the same thing. Okay, so this is less than or equal to n choose k, 2 to the 1 minus k choose 2. Okay, so the probability that the algorithm fails is less than 1. I mean, if this occurs, of course. So the probability that the algorithm fails is less than 1. Therefore, the probability that the algorithm succeeds is greater than 0. Now comes the magic. Here is the magic. The probability of success is 0, is greater than 0, is greater than 0. As a mathematician, that means that success exists. Success cannot be the empty set. There must be an existence of success. So it doesn't mean that the theorem is probably true. It means that the theorem is absolutely positively true. And the key word is exists. So the idea is you create a randomized, a random thing, or we will see a randomized algorithm, and it might succeed, it might fail, but if the probability of failure is less than 1, then the probability of success is greater than 0, and therefore success exists. So that is the basis of Erdős magic. If you do a little bit of calculation here, so a little bit of analysis using Stirling's formula. When you look at n choose k 2 to the 1 minus k choose 2 less than 1, and you let k go to infinity, you get that n is roughly constant k times square root of 2 to the k. Now actually this is to my mind, the major open question. The upper bound on n, which comes from the proof of Ramsey, is something like 4 to the k. And the lower bound here is like square root of 2 to the k. So there's a big, big gap between them. This gap has existed since 1947 because the 4 to the k was earlier. There have been some small improvements in lower order terms, but the gap between square root 2 and 4 has not moved. So this is a giant open problem. Here's a nice quote that I like from Manin, which speaks to the international nature of mathematics, and Erdős certainly had that international nature. Everywhere he would go, there was the chalk. There wasn't the computer. He was too early for the computer, but he actually wrote letters. Can you imagine that? People actually wrote letters in those days. So he wrote letters to people. And but this quote speaks to the international nature. I can come here, or you can come to New York, and we can just speak mathematics. I guess today we should write, the web looks the same in Moscow or Paris or Tokyo or anywhere. Okay. Just for fun, here's one about Mikhail Tal, the great, if I pronounce his name right, the great chess champion from Russia that I just like very much. So hopefully, I just read this recently and I thought it was pretty funny. So I don't know, something mysterious about mathematics, and I put that in. Okay, so here's what I mean by Erdős magic. If the probability that the random object has the property is positive, if there's a positive probability, then it must exist. So today, though, we have all these computers. Well, are they useful for anything? Well, maybe some things. I don't know. Some people here find them useful. I like computers for a very selfish reason, because I think the computers have led to very interesting mathematics, very interesting mathematics. There's lots of new topics that are being done using computers, certainly. Questions in computational complexity, many interesting mathematical areas have opened up because the computer exists. Mathematics is funny. In one sense, it's absolute. I mean, the truth is absolute, but where things come from, it comes from the real world, the problems we look at. And so now, in my lifetime, we have this new thing, the computer, and so we're getting lots of interesting new mathematics. And here's the modern way of looking at the Erdős magic. You create a randomized algorithm, and if you can show that the randomized algorithm has a positive probability of success, then success must exist. Indeed, sometimes I go back to the old papers and I look at how they're written, and they're written in some sequential form. And when I read the papers, I realize it's an algorithm, but they're just not using that language to describe it. But today, when people write papers, they immediately write them in terms of randomized algorithms, which is very good. Okay, so here's the problem, the main mathematical problem that I want to talk about. It was one of the favorite problems of Paul Erdős. And it's still very much an open question, 50 years old. So we have sets. Each set has n elements, and the number of sets is m. it's convenient to write m as 2 to the n minus 1 times k, just a convenient parameterization. But we don't know how many points there are, and we don't know if they intersect or don't intersect. All we know, very, very general, we have a certain number of sets, and each set has a certain number of points. But otherwise, no information about them. And what we want is to two-color the points, red and blue, in such a way that no set is monochromatic. Now, we can't always do that. We can't always do that. For example, suppose we had 2n minus 1 points, and we had all the subsets of size n. Well, then, no matter how you two-colored, some n points would be the same color. It would be monochromatic. So the first theorem was by Erdős in 1963, that if k is less than 1, then there exists a coloring. So for example, k equals 10, m equals 500. Each set has 10 elements. You have 500 sets. 500 is less than 512. So you have 500 sets. There exists a two-coloring of the points so that no set is monochromatic. And the proof is color the points at random. Each set is monochromatic with probability 2 over 2 to the n, so 2 to the 1 minus n. So you have failure for each set. Failure occurs with probability 2 to the 1 minus n. But then the expected number of failures, or just like here, actually it generalizes this result. The probability of failure is less than 1, so the probability of success is greater than 0. So the coloring exists. The coloring exists. I should mention there are a lot of very natural questions with Erdős magic about making an algorithm that works. And there are ways sometimes to take the randomized algorithm and change it to a deterministic algorithm. But I won't be doing that in this lecture. Okay. Now, the question that Erdős asked almost immediately was, what if m is bigger than 2 to the n? Bigger than 2 to the n minus 1. Maybe it's still true that you can find a coloring. So he asked the question, what is the biggest value of m? Thinking asymptotically in k. What is the biggest value of m? Thinking asymptotically in n. So if you like, what is the biggest value of k? Because it's a useful parameterization. What is the biggest value of k such that you still have a coloring? Now, the Erdős's proof doesn't work, but maybe there's some other method. Now, in 1964, Erdős found a family of sets of size, each set had size n, and the number of sets was 2 to the n squared, and there was no two coloring. That is, any two coloring did create a monochromatic set. So you can't take k equal n squared. So in 1963, he knew that if k is less than 1, there is a coloring. In 1964, he knew that there are examples where k is constant n squared, where there's no coloring. So what happens in the middle? And again, we're thinking of worst case. The sets are in the worst possible situation. Well, this has had a very long history. I mean, there are a lot of young people here, so, in mathematics, if you're banging your head against the wall and you like it, that's good. That means you'll be a good mathematician, because I have been working on this problem since, I think, 1970, and so far what I have is 0. I mean, I have no results on this. Very long, long history. But very, very interesting. And we now realize it's a deep, deep, deep question. There's something very deep about it. I think because there's no assumptions here. It's just there's no structure. So here's the history. Okay. In 1978, Joseph Beck, a Hungarian mathematician who's now at Rutgers University in New Jersey in the United States, improved the Erdős result. And he showed that if k was constant n to the 1/3, c means a explicit constant, but I just don't write down what it is. That if k was constant n to the 1/3, there still existed a color. And he found an argument for that. So that was a tremendous breakthrough. And then in 2000, Jacomar Radhakrishnan, who is at Tata Institute in, it's now called Mumbai. I think he's a dean now, I'm not sure. But anyway, he was actually a student of Semereti. Very interesting. He was a student of Andrei Semereti, and then he went to Mumbai. He's Indian by birth. And Aravan Srinivasan, who is also Indian, but he's now at University of Maryland in the United States. And they were able to improve this to almost square root of n. And that's as far as it went until last summer, when Jacob Kozik and Danila Cherkashin independently got the same result, but they got the book proof. They got the what we call the book proof, the beautiful proof. And I have to say, I was all prepared with this talk, and I did not know this, but Danila was the student of Andrei, right? So I promise you, that was not the reason I put this here. I didn't know he was your student, but I just think it's a tremendous, tremendous result. So now I want to show you the argument for it, and I give the algorithm is amazingly simple, but the analysis is not really complicated, but it's interesting. Okay. Let me first state the algorithm in a discrete way before we do this. We take the points and we shuffle the points. I have a little prop with me. Come prepared. Always bring a deck of cards to any talk. If you get bored, you can play cards. You know, it's very good. So first, let me give the discrete algorithm. You take the points and you shuffle them randomly. You put them in a random order. And now you look at, here is the algorithm. You look at the points one by one. And you do absolutely the simplest thing you can possibly do. You take the first point, red. Second point, red. Red, 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 red. But you come to a point and you can't make it red, because that will make a red set. Okay, make it blue. That's all. Nothing more. That's the algorithm. No cleverness. No cleverness. Just color red unless you can't color red, and then color blue. Okay? So that's the algorithm. And we want to analyze how well it does. Okay, well, here's the first analysis. I'll take out my cards. Well, whoop. Okay. Okay. How about the people over here? Are you okay? Okay. Okay. So again, this is a randomized algorithm, but all the randomization is in the random order. After you have the order, it's deterministic. So does it work? Well, maybe it doesn't work. But it can't create a red set. That's impossible, because if it would create a red set, you color the point blue. Okay, so maybe it colors a blue set. So maybe a set was blue, and look at the first point. Remember, they're in order. Look at the first point that was blue, all right, in the random ordering. Well, why was it blue? It was blue because it wasn't red. But we said color red unless you can't color red. So if this happened, there must have been a set E. I use E and F for the sets. That was red, 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 and then the last point, it had to be blue. And the last point of E was the first point of F. And if this happens, we write blame EF. And the idea is that set F blames set E because it's set E's fault for why F was monochromatic. Okay, what is the probability of blame of EF? Well, that's a difficult problem, but we can give an upper bound, and I can use my cards. So let us take n equals 14, and sorry, I had a joker, but I lost it. I really, anybody have a joker with them? I don't know if it'd be useful. Okay, well, this card is the joker. Okay, sorry. So here is a set, one set with 14 elements, the 13 diamonds and the heart. And so that's the set E. And here is the set F, the 13 spades and the special card, the ace of hearts. Okay. And what is the probability? Well, what is the probability that it looks like this? Well, we're taking the cards, and because we're randomly shuffling the big set of points, we're randomly shuffling these points. So the probability, so it's necessary that these are the first n minus 1 points, then this point, and then these are n minus 1. So therefore, the probability of blame is less than or equal to n minus 1 factorial times n minus 1 factorial over 2n minus 1 factorial. The sets each have n elements. So you have 2n minus, and they have to overlap in exactly one element, otherwise nothing happens. So there are 2n minus 1 factorial ways to shuffle. You need the first n minus 1 have to be all from E, so that's n minus 1 factorial ways. The second, the last n minus 1 have to be all from F. And their point of intersection has to be in the middle, but so you get this probability. And so what happens is that if m times m minus 1 times this, so this is the number of possible EF. So if this is less than 1, then the probability of failure, that's supposed to be a smiley face, the probability of failure is less than 1, so the probability of success is greater than 0, and so there exists a coloring. There exists a coloring. So this is a very nice, but actually this doesn't give the right result. When you do the analysis here, it gives, so the analysis means what is m as a function of n. So you do the analysis, and it ends up that m is, or you ask about k, m is 2 to the n minus 1 k. You get k is like n to the 1/4 when you do this analysis. So this does not actually give the result. In fact, it's weaker than the result of Beck, which was n to the 1/3. But here is but now we come to the idea of Kozik and Cherkashin. Though the algorithm is discrete, it's helpful to put it in continuous time. So I'm going to give exactly the same algorithm, but in a continuous framework. I'm going to give each point a birth time, which is uniform from 0 to 1. And now we start at time 0, and the time goes and the time goes from 0 to 1, and each point has a IID, a uniform independent birth time. And when a point is born, then you decide red or blue. But you see, it's the same algorithm because the points are in a random order. Equally likely, all the possible orders are equally likely. But it turns out that there's some nice analysis we can do that Kozik and Cherkashin did in this case. We look at so here are E and F, and they overlap in a point V, and we look at the birth time of V. And there are two cases. Either that birth time is very close to a half, or it's not very close to a half. So we will let the birth time we write the birth time as 1/2 times 1 plus x. So x is between -1 and +1. And we have two cases, near or far. So here's 1/2. In case 1, the birth time is not near, and in case 2, the birth time is near. Now, what do we mean by near? That's a parameter. We're going to say near means that it's between, near is case 2, that it's between 1 plus 1 minus p over 2 and 1 plus p over 2. We will do the entire analysis, and then we will choose the optimal p. Okay. So what happens? Suppose we are not near. Suppose we are not in the middle. Well, actually, there are two cases. We could be on the left or the right, so that there'll be a factor of 2 there. But if we're not in the middle, then what happens is we have this set X, this set E, and what we have is that all of the points of E are small, and the probability, let me call it left of E, meaning all the points of E are small, is 1 minus p over 2 to the n, less than or equal, actually equal to that. Okay, and so the probability of the union of left of E, well, here it's convenient that the number of sets is 2 to the n minus 1 times k, so the 2 to the n cancels the 2 to the n, and this is 1/2 k times 1 minus p to the n. Okay. So if a set is way to the probability that any set is way to the left is at most 1/2 k times 1 minus p to the n, and the probability that any set, the same argument on the other side, the probability that any set is way to the right is 1/2 k times 1 minus p to the n. So together, the probability that you have a set either way to the left or way to the right is k times 1 minus p to the n. Okay, less than or equal to, because we're always using the probability of a disjunction is less than or equal to the probabilities. So that's less than or equal to k times 1 minus p to the n. Well, that would be great. You just pick p large, and that'll be really, really small, except that's only case 1. Now we have to look at case 2, and case 2 is that this central point is near the middle, Now, what is the probability of that? Well, suppose the point is 1/2 times 1 plus x. Given where that point is, the other n minus 1 points maybe I left out the 2. Sorry, I left out the 2. Yeah. So given this point, we have n minus 1 points over here. So that's 1 minus x over 2 to the n minus 1. And we have n minus 1 points over here, which is 1 plus x over 2 to the n minus 1. But fortunately, 1 plus x over 2 times 1 minus x over 2 is less than or equal to 1/4. So therefore, this is less than or equal to 2 to the minus 2 to the n minus 1, which is what I wrote there. And so now, what is the probability? Well, the central point V has only probability p of actually being in that interval. The interval has length p, so that's probability p. And then wherever it is, you now have probability 2 to the minus 2 times n minus 1. But now we have to multiply it by the number of sets squared, because for each pair E and F, we have to look at this possibility. So we take that probability, so call this blame star. Blame star of EF is that F blames E and the central point is near the middle. So the union of the disjunction of the blame stars, we get the similar result. We get 2 to the n minus 1 times k squared times p, times this crucial p, times the 2 to the minus 2 times n minus 1. Again, the 2 to the n's cancel. This is why we did the parameterization in the first place. It makes it convenient. And what we get is k squared p. So the total probability of failure is less than or equal to k times 1 minus p to the n plus k squared p. And if that is less than 1, we're done, because this is an upper bound on failure. So if this probability is less than 1, I'll write less than or equal to 1, because it's equal to 1, you can do something. If this probability, k times 1 minus p to the n plus k squared p, is less than or equal to 1, then is strictly less than 1 to be formal, then the probability of failure is less than 1, and therefore the randomized algorithm succeeds with positive probability, and therefore Erdős magic, there exists a coloring. There exists a coloring. How do we find the right k and the right p? It's a very powerful technique. The older I get, the more I realize that calculus, I used to think calculus, I'm in combinatorics. Why do I care about calculus? You know, is it important? Turns out calculus is very useful. It's very useful even in discrete problems. It's good to know calculus. So don't forget your calculus. And you get a really amusing, I mean, if you want, just forget about the rest of the talk. Try and think of, this is a wonderful problem. I call it asymptotic calculus. Well, I would call it asymptotic calculus if, what happened here? Okay. Okay, so I love this problem. I mean, yeah, well, there it is, yeah. You want as an asymptotic function of n, you want k as an asymptotic function of n, and the question is, what is the largest k such that there exists a p in 0, 1 such that this inequality holds? How hard can it be? Pretty hard, pretty hard. This is really a wonderful puzzle problem. But if you don't want to do it yourself, give it to your high school friend.
We suppose p is a constant, right?
No, I don't assume p is. In fact, p is not a constant. No, in fact, in this problem, there's nothing. Notice in this problem, there's nothing about constant. No, in fact, p will be a function of n. P will definitely be a function of n. Yeah, yeah. So, which is a good point, because if p is a constant, then you'd be stuck. K would be at most p to the minus 2. So you want p to go to 0, but you want p to go to 0 slowly. And it turns out that this is the answer. And it turns out that p is roughly logarithm of n divided by n in the answer. But I leave this to you as a nice problem. A nice problem. I will tell you, if you try to do it exactly and you succeed, boy, then I'll really be impressed, because I've only done it by making a formal proof, but with inequalities that work. But I mean, technically, you would say, look, there's a function I can take the derivative, set it equal to 0. I've actually never been able to get that to work. But anyway, this is the result. So from this calculus result, we can take k to be constant root n over root log n. In fact, the constant is the same as the Radhakrishnan Srinivasan result. And then for that P and for that K, the probability of failure is less than 1. We can make it strictly less than 1 by some simple technical thing. And then the probability of failure is less than 1. Probability of success is greater than 0. Erdős magic, the coloring exists. And so that's the result. And that's the best result known until today. And so there's a gap between basically n to the 1/2 and n squared. And it remains a big open question, Here's another quotation I liked. I tried to give things a Russian motif. Well, actually Euler was Swiss, but he did his best work in St. Petersburg, so maybe he counts as an honorary Russian. I'm not sure, but here was his statement about prime numbers. I mean, I think prime numbers always have this wonderful mystery. For pretty much anyone that loves mathematics really should love prime numbers. I think it's almost a necessary condition, though not sufficient, but necessary condition. So here is a classic result. Look at the number of distinct prime factors of x. If you allow multiple factors, you get a similar result. But here, just consider distinct prime factors. And the result of Hardy and Ramanujan in 1920 was, to speak roughly, that most numbers x have roughly log n distinct prime factors. But what I want to do is give the proof of Paul Turan, another great Hungarian mathematician. Indeed, we celebrated the centennial of his birth a couple of years ago, and did a lot of work. And his proof really broke open new ground in an area that's called probabilistic number theory. So we pick a random number from 1 to n, and we look at its number of prime factors. So we let x sub p for p prime be the indicator function for p dividing x, and we let x be the total number of prime factors, except to make things a little bit easier, we stop at n to the 1/2. Now, asymptotically, that won't matter because no number can have more than 9 prime factors that are bigger than n to the 1/10. And asymptotically, that's just a constant that won't matter. So instead of looking at the total number of prime factors, we look at prime factors less than n to the 1/10. And what is the probability that p divides n? Well, it's roughly 1 over p. If you pick a random number from 1 to a billion, the probability that it's divisible by 3 is not exactly a third, but it's really, really close to a third. So it's like 1/3. But furthermore, and so what is the expected number? We sum p inverse over those primes, and we use a result from number theory that the sum of the reciprocals of the primes up to n is like log n. Okay, I'll just assume that fact from number theory. Okay. So the expectation is like log n, and now we want to look at the variance of x. The variance of x. The thing about the variance of x is that the covariances, if this is the term that's used, the covariances of these indicator random variables are nearly 0. Suppose we're picking a random number from 1 to a million. We look at divisibility by 3, it's nearly a third. Divisibility by 7 is nearly a seventh. Divisibility by 21 is nearly 1/21st. So it means they're almost independent. Of course, we have to be careful. I mean, we have to look at the error terms, but the covariances are pretty much zero, negligible, let's say. And so basically, the x sub p's are acting like independent random variables. And so the variance is just the sum of the variances, which is basically like the expectation. At least it's less than or equal to the expectation. If you have the sum of indicator random variables and they're mutually independent, the variance is the sum of the variances, but each variance of an indicator is less than or equal to the expectation of the indicator. And in fact, it's close. So what we get is that the variance is around log n. And then we use the theorem of Chebyshev that the probability of being more than k standard deviations off the mean is less than k to the minus 2. So if we let k slowly go to infinity, then like log n, then the probability that x lies between log n and log n plus square root log n times k and log n minus k square root log n is nearly 1, but that's saying that they're asymptotically log n. It's very interesting. He actually didn't use Chebyshev's theorem, and the problem was Kolmogorov. Kolmogorov was a great man, but would have been even greater had he been born 50 years earlier, because then we would have had his results even earlier. So Kolmogorov was getting these great results about probability, and more important, making probability a serious area of mathematics in the 1930s, basically. And this was done in 1934. So at the time, probability theory was a little, what can I say, suspicious. People didn't think, was that a real proof, or, you know, what was happening here? So actually, if you read his original paper, there's no probability in it. There's no probability in it. But when you read his paper, you can now see that what's going on is probability. And this is, I think, the proper way of looking at it. And then it was followed, I forget when this was, maybe 1960, I forget. Paul Erdős and Mark Kotz followed it up by showing that X has a Gaussian distribution. Oh, sorry, there shouldn't be absolute values there. It should be the probability that X is greater than expected value of X plus K root log n. So if you think, if the mean is mu and sigma is the standard deviation, it's really saying, let me say, we're saying that X, when you normalize X, you get the Gaussian distribution. The probability that X is greater than mu plus K sigma, that is for K fixed and n going to infinity, is the probability that the standard normal distribution, the Gaussian distribution, is greater than K. And actually, I mean, I won't give their proof, but it really follows the idea of Turan, except instead of just looking at the second moment, you have to look at the third moment and the fourth moment and the fifth moment. Indeed, you have to look at the rth moment for each fixed r. So you have this X, but you normalize it. You subtract mu and you divide by sigma. And you want to show that the rth moment is approaching the rth moment of the Gaussian. And it's a theorem in probability that if all the moments approach the standard Gaussian, then it approaches the Gaussian in distribution. Whereas Katz was a celebrated probabilist who grew up in Russia, I think. Not sure. Maybe Poland. I don't know. Okay. And so one has to look not only at the variance, but say at the fourth moment, fifth moment, sixth moment, etc. But if you look at the fourth moment, basically you have these indicator random variables, and you use the fact that roughly they're 4y's independent. That is, if you look at divisibility by P1 and divisibility by P2 and divisibility by P3 and divisibility by P4, the probability that it's acting as though each one was an independent random variable which was 1 with probability 1 over P. Okay. And that was the idea of their result, which was a tremendous result. I should say, Erdős didn't just work in this area. In 1999, 3 years after his death, Vera Schoch, one of his major collaborators and also a good friend, organized a memorial meeting in Budapest. And there were 15 lectures, and I had the great privilege to speak on this topic. But it was really amazing because there were 15 different areas, and in each area he had done so much great work. Here is a letter from him that I think also gives some of his spirit. So he was your age, right? He was born in 1913. That's pretty close, right? Yeah. And he was a prodigy. He was recognized at a very early age. The stories are that he was recognized at age 5, but certainly at an early age. And Hungary was a wonderful place for mathematics. It had a wonderful culture that supported mathematics. And so his talents, he could use his talents to the fullest. And PT is Turan Paul, is Paul Turan. So just writing to him about that. Well, what is it that draws us to mathematics? I think it's the notion of truth, the notion of absolute truth. For me, it came use the religious word epiphany. Can you translate that? Is that, I don't know. When you have a religious experience and you, okay. Yeah, so I had an epiphany when I was 16, 17 years old, and my teacher told me about the twin prime conjecture. That is, this conjecture, twin primes are like 101 and 103. They're both primes and they're exactly 2 apart. And the conjecture is, the conjecture is that there are an infinite number of them. In fact, I mean, in the last year or so, there's been some significant progress, but it remains a conjecture. And I tried to work on it, but I mean, of course, I didn't get anywhere. But the epiphany was that this is an absolute statement. That is, I have faith. My faith is that the answer is yes or no. I don't know which one it is, but that it's yes or no. Or to put it in a different way, I can imagine that there's another world where instead of carbon-based life forms, there's silicon-based life forms. I think the people at Yandex are working on that right now. I can even imagine a universe where we don't have inverse square gravitation, but we have inverse cube gravitational force. But I can't imagine that there's one universe where there are an infinite number of twin primes, and there's another universe where there's not an infinite number of twin primes. I have faith there's no God strong enough to do that. So that is my faith, but it turns out that not everybody agrees with this Platonist philosophy, and in particular, to make things a little lighter, let me point out something that one of your greatest writers once said, Dostoevsky. So here it is. Twice 2 makes 5 is indeed. I hope he. I asked him to find the original and write it. I only had the English, but anyway, it's. This has an interesting feeling in the other direction. So let's at least keep our sense of humor about things. One last mathematical thing that's a lot of fun. This is called the liar game. There are 2 players, Paul and Carol, but here I do need the English. There are actually 2 ways of spelling the word Carol in English. Usually it's C-A-R-O-L, but it is possible to spell it C-A-R-O-L-E, and we always spell it C-A-R-O-L-E. And if instead of doing the mathematics, if you have a good mind, you can quickly go through the 720 permutations, and at the end I'll ask, what is the permutation? Why is the reason that we put the E at the end of Carol? Because there is a permutation that the people at Yandex, you got it. So Andre got it immediately. It's Oracle, yes, okay. So we call them Paul and Carol, and this is the liar game. I put in specific numbers. Carol thinks of a number from 1 to 100. Paul asks 10 yes/no questions, but Carol can lie, but she can only lie at most once. And then who wins the game? And now at the end, it's not enough if Paul says, is the number 37, and Carol says yes. I mean, at the end of the game, we have a jury of mathematicians that look at the answers and decide if Paul knows the answer. And the theorem is that Carol wins. And the idea is it's a form of Erdős magic. So first of all, so Carol just plays randomly. In other words, Paul asks a question, is the number prime? Carol doesn't listen to Paul at all. She just flips a coin and says yes or no. So this is her randomized strategy. Now, there's a little bit of a problem with this randomized strategy, because maybe at the end of the game, we see that she has cheated. Because maybe the questions were, does x equal 15? Yes. Does x equal 15? Yes. Does x equal 15? No. Does x equal 15? No. So that would be cheating. But we can change the game a little bit. In fact, this is a meta theorem. You can change any game. You can allow Carol to cheat, but if she cheats, she loses. Okay? So with that modification, we let her play randomly. But with the understanding that if at the end there's no possible answer, then Paul has won. So at the end of the 10 questions, what's the probability that 37 is still alive? Well, there were 10 questions, and Carol didn't even look at the questions. So for each question, half the time she got it right, and half the time she got it wrong. but she was allowed one error. So the chance that 37 is still alive is 11 over 1024. Therefore, the expected number that are still alive is 100 times that, 1100 over 1024, which is greater than 1. The expectation is greater than 1. If the expectation is greater than 1, there is a probability that the number is actually greater than 1. So there is a chance, a positive chance, that at the end of the game, there are two possibilities. Another important theorem is that if an integer that's bigger than 1 is at least 2. This is an important theorem. So with positive probability, there are two possibilities. And if there are two possibilities, Paul has lost and Carol has won. So this says with this randomized strategy, with positive probability, Carol wins. But now comes the Erdős magic. This is a finite game. It's actually a complete information game because Carol doesn't really pick a number. Carol plays an adversary strategy. At each time, she can decide what answer she wants to do. So though when I first said it, it looked like there was randomness, there isn't. Carol plays an adversary strategy against Paul. So now it's a perfect information game. You have a finite perfect information game with no draws. That means either there's a strategy for Paul that wins 100% of the time, or there's a strategy for Carol that wins 100% of the time. There is a strategy for Carol that wins 1% of the time. Therefore, there's no strategy for Paul that wins 100% of the time. Therefore, there is a strategy for Carol that wins 100% of the time. And this is the proof by Erdős, a form of Erdős magic. And I should say, this can be de-randomized. One can actually give algorithms for Carol using weight functions, but I won't do it. So let me just finish first with my favorite non-mathematical quotation from the great South American author Jorge Luis Borges. This is from a wonderful collection in its Spanish title is Ficciones, but just if you haven't read Borges, I think everybody should read Dostoevsky, and every mathematician should read Borges. He has a mathematical mind, and this is a story. It's called The Library of Babel, and in this story, there's this universal library, and the librarian goes wandering around the library looking for the total book. I don't know how it got translated, but in English it's translated the total book, the book that has all the information. And he cries out that if it's so beautiful, I hope the translation is good. If honor and wisdom and happiness are not for me, let them be for others. May heaven exist, though my place be in hell. Beautiful, beautiful writing. Well, so this leads into my final story. It happened around 1985, and I took Paul Erdős to a camp for talented high school students in western Massachusetts, a summer camp. Had a funny name. It's called Yellow Pig Camp. So if you ever see somebody with a shirt with a yellow pig on it, you go talk to them about prime numbers. This was Yellow Pig Camp. That's what they called it. I don't know why. Anyway, we went up to the camp, and it was a beautiful, beautiful summer day, and Paul loved to talk to talented gymnasium students, high school students. He used the word epsilon. Epsilon meant a child. these were the epsilons. So he talked with them all day long. And in the evening, it came time to give his formal lecture. So the entire camp came to the center. And I had the honor to give the introduction. And in the introduction, I talked about the book. Some of you have heard about this. This was Paul's great contribution to mathematical theology, if that subject exists. He always talked about the book. In fact, I referenced the book proof that Danila and Jakob got. In the book, emphasis on not just a book, the book, there are all the theorems of mathematics. And for each theorem, there is only one proof in the book. And it is the deepest proof, the best proof, the most beautiful proof. He called it the book proof. And when we would be working on a problem and somebody found the solution, but the proof was, it was an ugly solution, but it was the first result, so he would be very happy. He never cared who did it. I mean, it was just important that that the solution was found. But he would say, okay, now we know it's true. Now let's look for the book proof. So in my introduction, I explained to these high school students about the book, but I made a mistake. I'm very glad I made this mistake. I said that the book is held by God. And it's in God's hands. It's not what I believe myself, but that's what I said. So Erdős got up to start the lecture, and Erdős never criticized anybody. I mean, that was never his style. He would always just be good. He was a kind man. He was always friendly to everybody, but he gave me a tiny bit of criticism, which I seriously deserved, that I will never forget. So he came up to start his lecture and he said, well, you don't have to believe in God, but you should believe in the book. So there we go, a little bit of philosophy for it. So, spasiba. Thank you very much.
Maybe some questions?
You told us about nice quotation from Dostoevsky, but
Yeah.
on slide it was written that it's quotation from Borges. So which quotation
That
is
was
it?
from Dostoevsky. That was a mistake by my translator.
Okay.
I was going to, what? Or did I get,
There was no mistake.
There was no?
There was a quotation from Dostoevsky, there was a quotation from Borges.
Oh, there were two quotations.
Two quotations
Oh, okay,
on
so-
different pages.
Okay.
well, I didn't know, but, and I should, in that case, I will thank,
I can just say in Russian.
Yeah.
Достоевский был из, как называется, записки из подполья, дважды два четыре.
Да, это была первая цитата.
Это первая цитата.
Нет.
Там был Хорхе Борхес, другая цитата.
Нет, перед второй цитатой было сказано, что это Достоевский. Или я неправильно
Почему?
понял?
Борхес было произнесено.
Ну все, хорошо, тогда
Нет,
я
там
прошу
написано
прощения.
было Борхес, а сказано, что Борхес.
Okay.
and let me thank Sasha Golevnev, if I'm saying his name right, who was from St. Petersburg.
No, everything was okay.
Oh, good. Okay, then in that case, I definitely thank him because he is from St. Petersburg. In fact, I just met his teacher. He was here on Friday, and he's now studying at New York University. I'm not his advisor, but I've worked with him, and besides doing good mathematics, he helped with the translation. So, thank you, Sasha.
More questions?
Moment.
And the proof of the Indian mathematicians,
Yeah.
Was it really tough? Or
Well, it was easier than Beck's proof, but it was harder than this proof. I can give you just the rough idea of the algorithm. They first they color randomly, and then they put it in random order. So that part is similar, and then they go through point by point. And if a point is dangerous, which has a technical definition, then they flip a second coin to decide whether to change its color. And but then again, they have to analyze it. I mean, one of the questions is they get the same results. So at some deep level, they should be the same proof, but they don't look like the same proof. I don't understand why they're getting the same results. And then their analysis is it's very good, but this is better. This is better. Yeah.
More questions? Maybe about history, about Erdős? No. Okay, tomorrow we will have another lecture. Maybe you will give its name, its famous.
Oh yeah. So let me just quickly say, tomorrow I will speak about large deviation bounds, but in particular with their applications to combinatorial problems, with their applications to what's called Erdős magic. Then on Wednesday, I will talk about percolation, which is always a wonderful topic. In particular, the main part, I will talk about the Erdős-Rényi model for random graphs and how there is this percolation place where earlier all the components are small, and then suddenly you get the giant component. So that will be on Wednesday. And then Thursday we will all go to Red Square to celebrate either the new Russia or the old Russia, or the new old Russia or the old new Russia, depending on how you want to look at it. And then Friday I will give a lecture about 0-1 laws, where the logic and the probability come together. So, and the three other lectures will not be this late. They will be at 3 o'clock, 3 o'clock in the afternoon. Okay. Спасибо.
Ну ладно, тогда до завтра.